So in that last problem, we didn't need to know the sum of the forces because the rotation gave us the entire solution because of everything we knew about the problem. But it's handy to write down the forces and the rotations each time because oftentimes you do need all of that information. And that's the case for our next example. This is problem 69 from your chapter. And we have I'm going to use my ruler here just so I can make this look nice. So we have a wall right here. And leaning against that wall is a ladder. And the ladder looks like this. Okay, so the ladder looks like that. And we are told that because it's just resting on this little point here, there's very little friction up at this point. But there is friction down here near this floor. And if we have this ladder leaning against the wall, the question is, what is the friction that the bottom is feeling, and how steeply or shallowly could I rest this ladder before it slipped? Okay, so we're trying to figure out the friction, and we're trying to figure out this angle down here. So we have that angle here. This ladder, we're told, is 4 meters long. So we have a 4-meter ladder. And we are also told that, so the center of mass of the ladder here is 2 meters from the floor, which means that this right here, we're told that it's up 1 meter above this point here. So this is 1 meter right here for a total of 4 meters. There's very little friction right there. And we know these distances. We'll call this one R1, we'll call this R2, and we'll call the total distance R3. And we're also told that it is 1.5 meters from the wall, so we'll call that R naught, let's say. Okay, so we know that R1 is equal to 1 meter, we know that R2 is equal to 2 meters, we know that R3 is equal to 3 meters. We're given the weight of the ladder, WL, is equal to 200 newtons. Okay, so again, we're going to try to find the frictional force that's happening right here. Remember, frictional force is proportional to the normal force. We'll call that normal force on the floor. And we have no friction acting up here. So let's go ahead and draw in our forces. Just sketch them in on this diagram to see what's going on. So there's going to be a normal force pushing up from the floor. We'll call that NF. And then there's a frictional force that is keeping this thing from sliding out from under us. So we're going to call that F, and it's going in opposite the direction of motion that this would slip if it did slip. So it has to be pulling this way to make sure it doesn't slip that way. And then those are proportional to each other by the coefficient of static friction. Now up here, there's no friction and therefore no forces in the y direction, so we only have a normal force due to the wall, and it's pointing out perpendicular to the floor. And that's because there's no friction. If there was friction, that force would be operating in the x and y dimension, but because there's no friction, it's just the force of the wall pushing on the ladder like that. So if I were to redraw that force diagram, I get something that looks like this. I get my normal force pointing like that. I get my weight of the ladder pointing like that. I get a normal force from the floor pointing up like that. Let's call this NW. And then we get our frictional force right there. Okay, so our first step with these problems is to write down our first condition of equilibrium, which is that the forces have to equal 0. So if I look at this, I have this force in the x direction balancing the frictional force down here, which is F, also in the negative x direction. So I'd write down that the x components tells me that the negative frictional force plus the wall force have to balance to 0, because those are the only forces operating in the x direction. And that tells us, if we put in our frictional force in terms of the normal force on the wall, plus the normal force of the wall equals 0, that means that there is a relationship between the normal force on the wall and the frictional force. So that's what we get from our x direction. From our y direction, if we look at this, we have the normal force on the ground is balanced by the weight of the ladder. And that's, if there was friction up here, that might take some of it away, but there is no friction there, so we just have the weight of the ladder being balanced by the normal force on the floor. So that tells me that the normal force on the floor pointing up is balanced by the weight of the ladder pulling down, and that's equal to 0, which means that my normal force is equal to the weight of the ladder on the floor. So I have a relationship. The first part of this question was asking us what is the relationship between the weight of the normal force on the floor and the normal force on the wall. And so we have a relationship for that because I can immediately calculate the normal force on the floor. That's just equal to 200 newtons. And then if I have the coefficient of static friction, then I can work out what the force on the wall is. But that's our next step, is to figure out what the coefficient of static friction is. So in order to do that, we're going to need some more equations. So here's where we put in the rotation. So I'm going to go ahead and draw this again, where we get the normal force due to the floor. We have our frictional force right there. We have our weight of our ladder right there. And we have our normal force on the wall. Now remember, because this is static, I can choose whatever axis I want to rotate around. And I'm going to choose this axis right here because that means I only have to figure out the rotation due to two forces, because any forces that are acting on the pivot point aren't going to actually show up in our equations, right? So I'm going to go ahead and just ignore those two forces and make this my pivot point. And when I do that, then I need to figure out the forces due to these two right here. Now these are not perpendicular, so I'm going to have to worry about the cross product here. So let me just go ahead and first of all figure out their signs. So the sign of this one, if I think about the direction that's operating, that's going to tend to make this thing pivot this way. So that, according to my right-hand rule, is clockwise. So we're going to call that a negative torque. So we're going to make that a negative torque. We'll call that TW. This one is going to tend to get it to pivot this way. So we're going to call that a positive torque, and we'll call that due to the torque due to WL. So that's going to be positive. Okay. So let's go ahead and figure out what these things are. So this torque from the wall is going to be, if I look at these angles here, we'll call that angle theta, we'll call this angle theta, and we'll call this angle, that would be what? 90 minus theta. Did I do that right? Yep, because those two lines are parallel. So my torque up here is going to be negative NW crossed into our R3, which is that right there. So I'm going to say R3, and then we're going to have a sine of theta in there, because we're going to have R crossed into our normal vector right there. So we're going to have the angle between them, which is the sine of theta. And it's in the negative direction because that's going to tend to rotate it clockwise. And now we're going to do the other force. That's going to be a positive, and I'm going to get WL, and this time we're just have R2 here, so that's going to be R2, and then we're going to have the sine of the angle between them, which is 90 minus theta. Okay, and that's got to be equal to 0. And I don't have to worry about these forces down here because they're around the pivot point, so the distance from the pivot point is 0. Okay, so let me re-simplify this a little bit. This can be written just as the cosine of theta, so I'm going to say, I'm going to bring this over to the other side, and I'm going to get NWR3 sine theta is equal to WLR2 cosine theta. Okay, and if I bring the cosine over here, then I can simplify that to just be NW R3 tangent of theta is equal to WL R2. Now if I look at what tangent of theta is, I can figure out what theta is because I had this triangle where we knew the distance here, R0. And that's my theta, and I know that this was R3. Okay, and to figure out the tangent of this, we need to figure out this side, but I can do that from Pythagorean's theorem. That's just going to be, if we'll call this, let's call this R height. So if I get R height squared plus R0 squared equals R3 squared, that means that this is going to be equal to the square root of R3 squared minus R0 squared. So I can get my tangent because I can do the opposite over adjacent. So that's going to be NW R3, and I'm going to get opposite, which is the square root of R3 squared minus R0 squared divided by the adjacent, which is R0, and that's got to be equal to the weight times R2. Okay, so now we know all of these things. It's a little bit of a messy equation, but we know all of these things. Let's just double check the units real quick. So I have the square root of a distance squared here, so that's a distance. I have a distance times a distance, which is distance squared, but I'm divided by a distance, which gives me a distance. And here I have force distance, so the units look good. So I call that okay. And then just to simplify that, write it down a little bit better, we're going to get NW is equal to R0 over R3 times R2 times 1 over the square root of R3 squared minus R0 squared times WL. I can go back to what I originally had, and we can figure out what the coefficient of friction is to make sure this thing doesn't slip. So I'm going to go ahead and write down that this is what we got from our forces, that this is also equal to mu times NF, but NF was equal to the weight of the ladder, so we're going to say this is mu WL. And so now I can plug that in on this side, and I'm going to get mu WL is equal to R0 R2 over R3 divided by the square root of R3 squared minus R0 squared times WL, and those are going to cancel, and then I'm going to wind up getting a unitless number, which is R0 R2 over R3, 1 divided by the square root of R3 squared minus R0 squared. So now let's go ahead and calculate out what the coefficient of static friction is. R0 was 1.5, looking at our triangle. R2 was 2 meters, R3 was 3 meters, and then I get 1 over the square root of 3 squared minus 1.5 squared. So 2 times 1.5 is 3, 3 is there, so I can just cancel those out, and that's going to give me 1 over the square root of 3 squared minus 1.5 squared, which is 2.25. So that's the same as 1 over the square root of 9 minus 2.25. And 9 minus 2.25 is, 6.75. So I get square root of 6.75. And I don't happen to have my calculator handy, but the square root of 9 is 3, and the square root of 4 is 2. So it's going to be somewhere between 2 and 3. So we know this is going to be something like, it's going to be less than 1/3, but it's going to be a number less than 1. It's going to be between 1/2 and 1/3, which is a reasonable number for the coefficient of friction.